This class coming up here is class F, Let There Be Light. And we take the Maxwell equations in differential form that we arrived at in the last class, and we do a theoretical play around with the equations, and we derive the wave equation for the electric and magnetic fields in free space. So free space refers to where there are no charges and currents where we're located. The charges and currents are somewhere else far away, but we're in vacuum in outer space, where there are no charges and there are no currents. So therefore we can simplify the Maxwell equations and the free space Maxwell equations. We will solve the free space Maxwell equations and show that they satisfy the electric and magnetic fields, that is, satisfy the wave equation. And then we'll find where the velocity of the wave is in the wave equation. And we'll show that it's related to the constants of electricity and magnetism. And this is a remarkable discovery historically, where when they put in the values for those constants, your epsilon naught and your mu naught, that you got the speed of light, or what they thought was close to the speed of light at the time. Later, Michelson measured the speed of light more accurately, and when he did, the constants really, basically, he nailed it. I mean, that's the speed of light, so light must be an electromagnetic wave. Remarkable. And the wave equation that we will derive is consistent with special relativity, which is also a remarkable feature, that when you look at the wave equation and have the speed of light in for the velocity of the wave, that equation is invariant under Lorentz transformation. So really, the wave equation, electromagnetic theory, and electromagnetic waves all point the way to the discovery of special relativity. And it was Einstein's insight to take the speed of light to be constant, and Einstein working more with Gedanken experiments, these like experiments in the head, imagine riding the light wave, and didn't make sense to him that light would be frozen, or the genius of Einstein to establish the special theory of relativity, which can be argued as a theoretical construct, not really traditionally from many experiments, with data and then finding equations that match. Of course, there's the Michelson-Morley experiment. One might say that's the data or that's the incentive. But if you look at Einstein's approach, it's very much thinking here in the purely theoretical sense, coming up with the postulates and then the theory of relativity. And general relativity also, just remarkable example of the power of theoretical physics. All right, well, we see the power of theoretical physics here as we introduce the realm of optics through electromagnetic theory and the Maxwell equations in free space, with their corresponding solution to show that the E and B fields satisfy the wave equation. Chapter F. Let there be light. We're going to start off, first of all, introducing the wave equation. And before we do that, let's consider a function here, say f of x, that has a peak at 0. In other words, f of 0 equals peak. Now, if you want to shift this function down to the right, a distance d, the way to do this is to have f of x be replaced by f of x minus d. Now you might say, why not x plus d? Well, watch. If this is a new function, say g of x, then if you put in g at the distance d down the road, you get f of d minus d, see in there, and that's f of 0, and that's equal to peak. So that shows that to go to the right, you want to have a minus sign. So when you put in x equal to d, you get f of 0. And you may be familiar with this sort of thing when you shift cosines and sines. For example, if you have here, say, the cosine, does this, right? That's the cosine, does something like this, the cosine of x. And if you were to shift the cosine a little bit to the right, so you would get here, this point moved over, say pi over 2, you would then get the sine of x. And see, that's taking the cosine and shifting it pi over 2. Now, since the cosine's an even function, you can write this as the cosine of pi over 2 minus x. That's probably the way you remembered it, that if you have two angles and they make 90, they're complements, then the sine of one angle is going to be the cosine of the other one, the pi over 2 minus x. So you've seen that shift idea. Now what we're going to do, let it move down the road. So we're making a pulse, a traveling pulse. We want to find the wave first, then we'll get the wave equation. So if we have, say, for example, and this is the psi Greek letter that's often used for a wave, if you have some f of x and make that d of vt, then this would be a disturbance traveling down to the right, down the x-axis. And we'd like to find an equation for this. So let u equal this, and let's take some derivatives to come up with a differential equation. Now the partial of u with respect to x would be 1, and the partial of u with respect to t would be minus v. So you could doctor this up so that we have a differential equation that will work. For example, if you take the partial with respect to x, you would have here the partial of f with respect to x, and then I would use the chain rule and say this would be a df of u, say du, and then the partial of u with respect to x. So this would be df du times 1. Then if you had the partial with respect to t and did the same thing, you would want df du and then the partial of u with respect to t. That would be df du, because we don't know what f is. And then here's the minus v. So you can make a differential equation and say that the partial of psi with respect to x, you would need to have this minus v in there. So that would be, to get that minus v in there, what you would do is, if you had, say, this x1, and you have this one, you need to get rid of that. You need to get rid of this. Okay, so in other words, to have the df du, just divide. So this would be minus 1 over v, the partial. So this would work out because this d side, partial psi with respect to x is df du, and then the partial of psi with respect to t dividing by the minus v, we'd get to the same thing. However, this is not desirable because you would have a different equation for one traveling the other direction. In other words, you'd have, if you had, this is one traveling to the right. If you had one traveling to the left, you would need to have a plus v. We don't want two differential equations for the same, wave equation. We don't want a direction to be important. So therefore, we would go to a second derivative, and the second derivative would get rid of that for us. So if we did, for example, the second derivative with respect to x, then we would have the partial of, we had here d f du, so we're just going to basically do this. So this will be the second derivative of f with respect to u, and the partial of u with respect to x, which is a 1. So this is the second derivative of f with respect to u. And then if we did the same thing with the time, we would want the partial, and here this is going to be df du with the minus v in there. So what'll happen here is you'll get the second derivative of f with respect to u, and then when you do the chain rule, you'll get another negative v, and you get the v squared. So then what you do is you can write this as the second derivative with respect to x. Now you divide by the v squared, and you have a nice equation. And that doesn't matter if v is plus or minus, you get the same differential equation. So that's the wave equation right here. Now, my mentor at University of Maryland had a cool way of remembering this. He basically said distance, like x, is velocity times time. So that means when you have the x, a meter squared down here, or just think x is vt. So in other words, to make the units come out, forget that they're squared for now. Just look at this relation here. X is vt. So the v has to go with the t. And the solution would be, and with differential equations have like second order, you expect two solutions. So here is one, the wave traveling to the right, and here is a wave traveling to the left. See, that's nice. Now what's really neat about this is that you can do two things. First, we can easily generalize to the 3 dimensions. So for example, if we had the 3 dimensions, we would have the second derivative of each of the 3 x, y, and z dimensions like this. And this would be now a wave in 3 dimensions rather than just traveling down the road. And if you remember that the del here from the last class is I hat d dx plus j hat d dy plus k hat d dz, then if you take del dot del, then when you have this twice, like this, plus I, like that, just go ahead and write it out again. And then dot, same thing, like this. You're going to get contributions with I dot I, because I dot j is 0, I dot k is 0. You'll get this one, will be a 1, and you'll get this one. But what is this? Second derivative, because I dot I is 1, so you'll just have the second derivative. So you'll basically get here the second derivative with respect to x. Then this is an operator equation. This is an operator. That's what you'll wind up getting as these dot to get 1s, and then you'll just have the 2 derivatives together, second derivative. So that means this thing can be written as del squared, or that's called the Laplacian, by the way. And that's equal to 1 over v squared, second derivative, respect to time. Now, what's very fascinating about this, that's the second thing that's very, very fascinating about this, is that if you put in the speed of light for v, so that you have, say, del squared, like this, equals 1 over c squared, notice that you have the c with the t, and these are, if you look over here, it's probably easier to see, these are the spatial dimensions, and they're squared here dimensionally. And then here you have the speed of light, and this is like relativity. So if you are actually wanted to subtract, say, like this here, And in our case, I think we had the t as a positive. So let's just put the t, first like this, and then subtract like this. You have something that looks like the invariance in relativity, where you have, remember we had the c squared dt squared minus, dx squared equal to a constant. In other words, this didn't change. Then you had the minus y squared minus z squared ds squared, like some kind of length in special relativity. And this wave equation with the speed of light in there is in agreement with relativity. But even though this equation had been known before relativity, it would take an Einstein to say that this speed for light, the v, is a constant. In other words, it's the same for all frames of reference. Then the Lorentz transformation, if you use it because of this appearance of the space and time in this fashion with the minus sign, you can show that this equation would be the same with the primes, t prime and x prime, y prime and z prime, and the speed of light would be the same. So the secret, and when we do electromagnetic theory now and show that we can get the wave equation, this wave equation, from the Maxwell equations, that is more of a push toward relativity eventually, going to be discovered by somebody. And when we go to F2 here, which we'll call let there be light, I'm going to show you that if you have the laws of electricity and magnetism, you have light. We're going to show that light comes out, a wave comes out, electromagnetic waves come out of electromagnetic theory. And then the famous shirt. And God said, and these are the Maxwell equations, and there was light. Isn't that cool? So that's the brother, an engineer. Here's the sister, a astrophysics major. And then we have finally the little baby brother or baby sister, the baby version. All right, isn't that nice? Some of these units in these equations may be a little different. There's the MKS units. We've been using MKS units for the Maxwell equations, but there are other systems of units, so don't be concerned if you find a little variation in how the equations are there. So here's what we do for let there be light. We go to the Maxwell equations. Del dot E is rho over epsilon naught. Del dot B is equal to 0. And then del cross B is mu naught J plus mu naught epsilon naught, the partial. Okay, now this is from our last class. And then finally, Faraday. So this is Gauss's law. It comes from Gauss's law, Coulomb's law. This is no magnetic monopoles. This here would be Ampere's law plus a displacement current piece that was added by Maxwell. And this is Faraday's law. Now we're interested in the Maxwell equations in space, in free space. So the free space Maxwell equations have no charge. In other words, we're far away from the charge. We're far away from any currents. So that means this one is going to be 0. This one already is 0. Del cross B, there's no currents where we are, so this will simply be mu naught epsilon naught and the partial v respect to t. And this last one has no currents or charge in there, so we're fine. So these are the free space Maxwell equations, and we would like to solve these equations and show that E and B satisfy the wave equation. All right. So free space means that rho is 0 where we are, and the currents are 0 where we are. So we're in like a vacuum, far away from the sources. But you need the sources to generate electric magnetic wave. You'll take like an electron or something and have it accelerate. So you do want to have them somewhere, but not where we are. Where we are is just going to be the pure wave, and I'm going to show you it's an E&M wave that's going to go by. Now we want to show that the electric and magnetic fields satisfy the wave equation. And we're going to do this in a very sophisticated way using the differential form of the Maxwell equations. So since we are aiming for a wave equation, and this is the wave equation, and this is a nice example of theoretical physics, like we're playing around with the equations to try to derive something that looks like this. Or you may have been just playing with the equations to try to discover something, and you stumble on an equation that looks like this, all right? So, either way. So we're going to look for manipulation of these mathematically to see if we can get a wave equation. So first thing we're going to do is say, well, I have the second derivative here, so let's take one of these. Let's take this one, and let's go ahead and on this one, since we have the first derivative, let's take a derivative to get the second derivative, because you have second derivatives here. So if we take the second derivative of del cross B, then on the right-hand side, we'll have the second derivative. We're really taking the second derivative on the right-hand side. On the left-hand side, we get this weird thing. So we're really taking one derivative on either side with the aim that on the right side, since we already have one derivative with respect to time, we'll get the second derivative. So just look at the right-hand side, one derivative, we're going to take another derivative with respect to t to get this kind of thing. All right, then we're going to see if that on the left side can become that. And then look what the speed of light is, in terms of constants. That's awesome. So here, what we'll do is we'll move this inside. So this is space and time. We're going to be independent variables here. So we can come in here and do the second derivative, first derivative. We do the first derivative here, and that's mu naught epsilon naught, and that's the second derivative with respect to time. And then we say, well, what about this thing? Well, see, we're going to be using this equation here so that we can get back to have just e's. That's the idea. So by using this equation, we're going to put in then for the derivative of b with respect to t, we're going to put in a minus the curl. So this is then minus the curl like this, and that's mu naught epsilon naught, and the second derivative with respect to time. Now, the intro books in physics, if you happen to have taken intro physics too, they will talk about the wave equation, but not do it in this sophisticated way using the Maxwell equations in differential form. They'll use the integral form. So that's cool to have more than one way to do things. Okay, so here, this will be then, we forgot here there's a curl. There is this curl here that we don't want to forget there. So looking at this thing here, you're basically taking the curl cross, and that derivative is going to be minus the curl of E. So that's what we got here on the left-hand side. So now if we multiply by -1 on both sides of the equation, we have a minus sign here like this. And the rest of this derivation is going to involve messing with this left-hand side. It looks a little weird. Well, this is right here already pretty complicated, because this is going to be a I hat, J hat, K hat, I'm setting up my curl with the determinant, and this is then EX, EY, and EZ. Then this will be here, the partial of the EZ with respect to Y, and minus, you flip them, EY, EZ, like that. And then we'll have here minus j hat plus minus part of that, and then we do these two. So that's the e z with respect to x, and then we want to flip them. And then the last one, this one here, plus minus plus, now we're going to do these like that. So that's going to be the partial of ey with respect to x minus, and then we flip them, ex with respect to ey. So there we have, and we did this last class. So this is just a review of last class, how to take the curl. But now the problem is, you got to take the curl of a curl. All right, so that means if we do this thing, say I hat, j hat, k hat, now we have to write down these three things down in here. So here is, say, z with respect to y minus uy with respect to z. You know, some cool notation, like here I want the partial of ex with respect to z. I could put down ex comma z like that, and then subtract ez comma x. So that's a little shorthand notation, and this last one would be ey comma x minus ex comma y. So a little trick there. So here we have the partial of ez with respect to y minus, and then flip. And then here I have the plus one is the x one with respect to z, and then minus the z with respect to x. And then here the y one with respect to x, and then flip it. So a little shorthand notation there. So let's do the first component. Let's go del cross E. If we do the x component, we're going to be able to understand what's going on rather than do all three. So the first component, you know, that's when you take this thing and cross out that, and you're going to be doing these. You're going to have the partial of y on this thing, and I'll go ahead and write these out. This is ey with respect to x, and then minus the ex with respect to y, and then subtract. So for the I hat, we're working with, say, this grouping or a cofactor, like in determinant, you know, terminology. So you have d dy of this thing, that's the partial of y with respect to x, and then minus, you flip it, and then minus, you're going to go this way, the partial with respect to z, and here this is the partial of ex with respect to z, and then minus, you're going to flip them, the z and then the x. So that's the component, the first one, and then this would be the second derivative here. We come in here, we got partials, you get y and x, and then here, this one's going to be the second derivative with respect to y, since there's two y's. And then here, this is going to be the second derivative with respect to z. And this last one's a plus sign, second derivative, and that's going to be partials z and x. Now, since the order of differentiation doesn't matter, we can write this as flip. Put the x one first, like that, and then minus here. We got this, and then here, second derivative ex, and then z, and then plus second derivative with the ez. We'll put the x one first. Okay, what's next? Well, what's next? We're going to do a kind of factoring. Take the partial with respect to x. It's a little rearrangement. And then here's y with respect to y. That's that one. And then here, we're going to put this next one from over here. This will be then the partial of ez with respect to z, like that. and then minus the other two terms. There's x, and here is x again. See, when you're playing around in physics, like if you're doing experiments, you play around, you try different things, see what works. And with theoretical physics, like you're playing around. So this is the result of playing around. So this may have taken like hours and hours or days, or weeks and weeks playing around with equation, trying this, trying that, and seeing how we can simplify. So by playing around and getting this far, we can see here that what the next step is that we do is we're going to add and subtract the third one. So here is the x one. We have a y and a z, so we're going to put an x1 in there like this. And then we have to subtract. But if we subtract, see, that's the second derivative of the ex with respect to x. But look at this. These are the other ones. We have the second derivative of ex with the y, and here is one with the z. Isn't that cool? And now we see that this is the divergence. That's the divergence, the del dot E. Remember that this is here I hat d dx plus j hat d dy plus k hat d dz. And if you dot that here with ex I hat plus ey j hat plus ez k hat, the ones that are going to contribute are the I and the j and the k. But then look at these. I dot I is 1. That's just a partial derivative of Vx with respect to x. That's what this is. And the next one's a partial derivative of the Ey one with respect to y. The last one is the z's. So, and this is 0. Why? Maxwell equation. Free space Maxwell equation. Remember? Del dot E is this, but in free space, that goes 0. That's 0. We're in free space. Big time simplification. And look here, bonus. The second thing is here, essentially, in fact, we'll go ahead and write this out again. This is del, this curl of a curl. X component is partial with x, the divergence, minus, but see what that is the Laplacian working on that, which we saw earlier. Up here, see? If you have something at the top here and you have x, y, and z, then it's going to be del squared, the Laplacian, working on whatever's at the top. So here, what's at the top is this ex, and then you have the x, y, and z, second derivative. So this is going to be, the psi is going to be here, ex. And then this is 0. All right. Now, do we really need to do the y case? What we would get if we did the y case? Wouldn't we get minus del squared ey? And then if we did the z case, we'd get del squared ez. So in other words, we could write down for the vector form, the complete form of this whole thing. This is really going to be equal to a minus del squared operating on each of the components, x, y, and z. I'm putting in the I hat. In other words, we're putting in the I hat and the j hat and the k hat. So if we do that, put the I hat here, then the I hat goes there. But see, if you have here, the EX goes with the I hat, so that's what it is. And then we have here with the J hat, you would have, that's the next one. So basically that is your answer. That's what you got there. Notice if you put the I hat here, then this the partial derivative of something with the I hat, that's actually a gradient. So if you wanted to write down this before the 0, you would write down, this is the gradient of, now we don't really need to do this, all right, because we already have the answer and we know that this is 0. But you could write this as a vector equation because, see, these are vectors with I, j hat, and k hat on either side, if you wanted to, but really we don't need to do that. So let's go back up here. We have shown that this on the left-hand side is equal to minus del squared the E vector. But that's it. Like the minus signs are going to cancel. Boy, it's really nice that that was a minus sign. All right. So because we have that minus sign, it's going to cancel. And then what we're going to get here is the del squared on the E vector is going to be mu naught epsilon naught and the second derivative. And this is the wave equation up here where the 1 over c squared has to be the mu naught epsilon naught, like this. That's the velocity. So in other words, the velocity of these waves is going to be 1 over the square root of mu naught epsilon naught. And then one of the most remarkable then plugins in the history of physics is when you plug in the numbers that you know from electricity and magnetism. Remember, epsilon naught goes with electricity, and the mu naught appears here, you know, with the magnetic force here. You're basically having these two constants that come out of electricity and magnetism. When you put the numbers in, you get something that at the time looked very suspiciously close to the actual speed of light. That is wild. And notice that the speed of light is written in terms of constants, electromagnetic constants. So Einstein's considering C as a constant, wow, has some kind of cool philosophical meaning here that, well, you can write it in terms of constants, but does that mean it really is constant, like from all frames of reference? Well, Einstein said yes. And there you have special relativity. Okay, so now what I would like to do is deal with the magnetic field. What did we do for the calculation? Let's just summarize what we did. We looked at something like this. And we took a derivative so that we could get another time derivative in there, like this. And then we were able to put in what this thing is. In other words, here, this thing, we're looking at the equation, this equation here, where the partial of B with respect to t is minus the curl. And when that went in, up in here, we then got the equation with the minus curl, we're just plugging in here. And that would give us the mu naught epsilon naught, the second derivative with respect to time. Okay, then we went ahead and showed that that got us the wave equation. Well, now let's go ahead and look at the equation with the curl of the E. Well, that's going to be this one here. That's going to be minus dB dt. And then if we do the same trick with the derivative, we would then have, just copying here, the similarity. And what I have on the right-hand side now, using this same trick, would be then the second derivative of B with respect to time. Then what did we do? We looked at the derivative of b with respect to t. Now we want to look at the derivative of e with respect to t. And that would be this one up in here. And that is equal to 1 over epsilon naught, u naught, epsilon naught. And that is then the curl of b. So when we plug that in, the same kind of steps, this is going to go in, for here. Then we're going to get del, see a curl of a curl, like we did before. And this is going to be the over u naught epsilon naught. And here we have a minus second derivative with respect to b. Okay, but now, if we compare these two, these are the same, just with the b replacing here, because see, if you replace the e with the b, you have here the minus sign, here's the minus sign, and then you have here this combination, well, you can bring it over to the right. You have here the same thing with the b. So this equation is the same as that, which means we could do all the same steps again and find that we will get, for the magnetic field, we'll get the same thing. Save us a lot of trouble. In other words, the magnetic field also satisfies the wave equation with the same velocity, the same speed of light, because of the similarity here. Del, curl, a minus sign here, and a minus sign over there. And then the e is the b, second derivative. This thing is this here, it can come over there. So these are the same, and that's what we did over here, and then did all these steps to get the result. So we have shown that the wave equation is satisfied for both the electric and the magnetic fields. So F3, E&M Waves. Now I would like to show that the waves are doubly transverse. In other words, if you have x, y, and z, you could always have a coordinate system as long as when you take, say, I hat cross j hat, you're going to get k hat. So this is the same basically as you might do something like this, x, y, z. We just simply turned it so x is up, y is out, and z is to the right. I basically want to show that if the electric field is, say, along here, that the magnetic field will be this way, and that the wave will travel to the right. So to show this in general, the speed of case, we should start with an E that has, say, a transverse component, x or y, we'll pick x, and a parallel component. See, if the wave were to actually oscillate this way and move that way, that's like a sound wave, that's longitudinal. If it goes this way, perpendicular, and travels that way, that is a transverse wave. So we're going to have both in here just because we're not sure. And then to have the simplest wave is going to be a sine, say, simplest function, oscillation, z minus ct. So we're traveling here down the z-axis at speed c. We're basically dressing up the sine wave. So in other words, sine of x, we're going to want to use sine of kx. And now if you have x is in meters, then k will be 1 over meters, so that we can then apply the sine wave, because the argument for the sine wave has to be dimensionless. And that will be the way to dress up. We're dressing up the sine wave for physics. And you could also put in an amplitude there, which is important in physics. Like in a sound wave, that's going to relate to the volume, how loud something is, and with light, like how bright, it's going to be related to the brightness. So we get that. Now we need to have traveling motion. That is very powerful. And I could then here take my x minus d, and now I have a sine wave shifted to the right. So now all I got to do is let d equal velocity times time, and I'm trucking along. So our function here, if I just want to write down the one going to the right, let's say, and we have the amplitude, here we have a, and we can have sine, and then this would be k. So now let's study this function a little bit. And to study this, what we're going to do is we're going to let t equals 0 to freeze it. If t is equal to 0 and I freeze it, I have a sine of kx. All right, so here is then the sine, like that. And this is then the function, this function here. This is x. And this here is your amplitude, how tall the wave is. Now notice that the definition of the wavelength in physics is one picture pattern, one cycle. And notice that one cycle for the sine function, you're going to get that when the sine is of 2 pi. That's when you're going to start again. See, so now we're using our math. When the kx is going to be 2 pi, that's when we're going to start again. So that means the k is the 2 pi over lambda. This is the general wave. And then for the b, since we don't know anything about the b, we'll say here I hat and a j hat and a k hat. And when we put the sine function here, we should be careful and add some kind of phase because they may not be in phase. All right. So the first step is to consider del dot E. This is like step A equal to 0. So if you do that, that would mean I hat d dx plus j hat d dy plus k hat d dz. That would be dotted with what we have up here, which would be ex I hat plus ez k hat, and the sine k z minus ct equals, that should be 0. So this is what I'm using here. So if I come in here, I dot I, this is how this will be working, and then the k will work with the k. So this will be the derivative with respect to x, but see, ex and ez, these are constant amplitudes because the time dependence is over here. So that, and there's no x's here anywhere. So that means that you're going to get 0 for the x derivative. So in other words, if we were to work this out, del dot E here, we work this out, we would get 0 times, when you have the I dot the I, you'll get 1, but then when you take the derivative of ex with that, it's going to be 0 because there's no x dependence. Then for the next one, what you would do, now this k is not anything, it's not like k hat's something else, so don't worry about that. There's just some constant here in there. Okay, so then what we do is we take the derivative with respect to z. Actually, what will happen here is we'll get a cosine. This is kz minus ct, and we'll pull out a k, and there'll be an ez floating around. So the derivative with respect to z, since ez is an amplitude, you can pull that out, and the derivative of here would be the cosine. Using the chamber, we'll pull the k out, and then this would be here the k unit vector dot the k unit vector, which is going to be 1. This has to be 0. Well, since this is fluctuating, this is arbitrary, to make this work, this EZ has to be 0. In other words, there's no amplitude in the direction of the wave. So that means it's not longitudinal. This proves that light is transverse, and we need to do that to make to complete the description of the light wave. So the conclusion is you can have the EX one or an EY one. I didn't include an EY one because I just wanted one transverse and one longitudinal parallel, a perpendicular and parallel. I'm covered. And so here we can have the EX, or we can have the EY, you can have something in a combination. That's called the polarization, by the way, the polarization of the light. So we got that. That's good. Now, if we use B, here the divergence of B must also equal 0 from the other Maxwell equation. That's going to show that the BZ is equal to 0. So in other words, the same argument, same logic is going to apply, and that's going to show that that B doesn't have a parallel component, that B is also transverse. Now we'd like to go ahead and find out more about B. So what we'll do is we'll look at here this Maxwell equation, which we have used, all right? We'll look at this one, see what that teaches us. Okay, well, what do we have so far? We have for the E, just the EX amplitude, and we have the sine, K, Z minus CT, and the I hat. So if we take this curl, we'll go ahead and write down the determinant. Just have something over here, the EX sine. You have a 0 there and a 0 there. Just have like an I component. So when we're doing this, the I hat would be just 0 and 0, so like nothing there. And the J hat would be, you would take this derivative. So we're gonna have a J hat. K hat, by the way, this is a 0, and since there's no Y in here, that's 0. So really, we're gonna be looking at here the J hat. So here is plus, minus, plus, so we put a minus J hat like that. Then it'll be the partial of X working on 0. And then it'll be the partial of Z working on this thing over here, the EX, the sine of KZ minus CT, like that. So this is gone, and then these minus signs cancel, and then I'll have an EX. If I take the derivative here, I'll get a cosine. And then a K will pop out. So this is what I'll have. I have the EX, that's just an amplitude constant. And then we'll have the derivative of this with respect to Z, which gets cosine, chain rule pulls out a K, and then the two minus signs cancel. And then for the magnetic field that we had from before, we said it had to be transverse. So that means no Z component. So we have this, and then we have the sine, Z minus CT, and then we have a possible phase in there like that. But see, this has to be minus dB dt. So if we were to take a derivative of this thing, minus dB dt, we would have here a minus sign, and since these are constant amplitudes, These would stay there, and we would then take the derivative to get the cosine, kz minus et plus the phase, and then the chain rule, there'd be a minus kc coming out of there. You take the derivative, you get the cosine, and then the chain rule minus kc. So if we clean this up a little bit, we see the minus signs would cancel, and the kc, I put it out in front, kc, and then I have bx I hat plus by j hat cosine k z minus ct plus the delta. And this, this derivative here is supposed to be, it needs to be equal to that, what I figured out up here, which I figured out, here it is, I figured this out. So that minus that derivative, that has to equal the curl of E, which I'll just copy over again. That's an EX cosine KZ minus CT. So EX, a cosine, and then there's a K floating around, and then there's a J hat. Okay, so here you can see that there's no I hat here. So since there's no I hat here, that means Bx is 0, because this is a vector equation. I hat has to equal I hat. There's no I hat here. See, this is plus 0 times I hat. So that means Bx is 0. Notice that the cosines are there, but the phase is gone. This delta's got to be 0, since there's no delta down here. And then here, this K cancels this K. And then what's left is CBY. So CBY, that has to equal the EX. So BY equals EX divided by C. Wow, delta is equal to 0. BX is equal to 0. So we have shown here that if the electric field is along the X direction, like this, then the B field is a Y. It's along here. Nice. And the direction of propagation is this way. This is where we're this is the travel direction. So we travel this way. And notice that the magnetic field is suppressed in terms of the speed of light's being very large. So that's interesting also. So that shows that we have a transverse wave, doubly transverse with the electric and magnetic fields. Now, I would like to just point out, very profound about these equations, because this is saying that a changing electric field creates a magnetic field. And this says a changing magnetic field creates an electric field. See, that's how you get the propagation of light. You need that displacement term that was added by Maxwell to get the self-propagation, and you need no medium, travels in vacuum. And this curl could be thought of as like a crisscross thing, which gives you that perpendicularity. In other words, if you have the electric field, changing this way, it creates a magnetic field perpendicular, which then creates an electric field, and a magnetic field, and an electric field. You propagate this way at the speed of light. And that helps us understand here this transverse nature being this perpendicular nature. So the electric field, so you take a charge, for example, that sets up electric field, but then if you wiggle it like this, you shake off waves, and then the magnetic field, say, will be perpendicular to it. So you get this transverse nature. And you basically shake a charge or shake a magnet, mainly it's going to be charges. And that gives us the rich electromagnetic spectrum here, where the visible spectrum is a very small part of the spectrum. So here the wavelength increases to the right and the frequency increases to the left. So that's like the Roy G. Biv going that way. And here you're going, I mean, you're talking like something like 10 to the like 15 or something, you know, cycles per second. I mean, you're going crazy here. The radio waves, which are very, very long, you go 1,000,000 times a second, you get radio waves. So here you have your visible narrow spectrum, and then your infrared, microwaves, and radio waves. Got FM and AM in there. And this is all the different frequencies of electromagnetic waves. Then you have ultraviolet on this side, X-rays and gamma rays. They're very rich spectrum. And here's a nice little picture. So you have the E and the B field, the electric field, traveling, the sine wave here. You know, sine waves, natural motion. Atoms like to vibrate, charges like to vibrate with sine waves. So sine waves, good choice. And there's your sine wave, the electric field, and the magnetic field in phase. Remember, there was delta was 0, and look at that, say perpendicular, and the propagation down to the z-axis to the right. There's your wavelength, you know, where you have one cycle. Very, very beautiful. Whole realm of physics opens now. The realm of optics, electromagnetic waves, visible and invisible light.